let's get to those examples. We just learned the net change theorem, that if we take the definite integral of a rate, we end up with net displacement. And if we were thinking maybe like miles per hour, then our displacement would be how many miles we went. Here's one with a little bit different context. Let's say if water drains from a tank at a rate of W of T liters per minute, what does this integral represent? And you see we have the definite integral from 4 to 10 W of T dt. Water drains from a tank, so we've got this big tank. There's maybe hundreds of liters of water inside this thing. W of T is the rate at which the water is pouring out of it, is draining out of it. So what does that integral represent? Let's think about the units. What are the units for W of T? Well, they tell us in the question, the units for W of T, liters per minute. What are the, so that'd be like the height. What are the units of T? Well, minutes, right? So if you think W of T is being multiplied with dt, literally think about the units there. W of T is liters per minute. dt is the units of time, minutes. So W of T times dt, obviously we would just get liters here. Okay, so it's something just with liters. It's like the number of liters that have drained out, but we can be a little bit more specific than that. What do the 4 and the 10 represent? Okay, the 4 and the 10 take on the same units as the T. Those are T values. They're like numbers along the x-axis or the t-axis here. So the 4 is 4 minutes. The 10 is 10 minutes. So what does that represent? It's the number of liters that have drained out starting 4 minutes after time was whatever we're saying time 0 was, probably when it started draining out to begin with, we'd say, all the way up to the 10-minute. Maybe you could say it like this: the number of liters drained from the 4-minute mark to the 10-minute mark. We'd want to be more specific. You know, some people might say, well, could we say it's the number of liters drained out during those 6 minutes from 4 to 10? Like, yes, but we want to include the fact that it's from the 4-minute mark to the 10-minute mark. It could be that water drains faster at the beginning and then it slows down. We don't know. So we'd want to be real specific and say from the 4-minute mark to the 10-minute mark. Okay, and this example will now actually have us do some details here and do some integration, plug some numbers in. Let's see it. The velocity in meters per second of a particle along a straight line is given by v of t equals t squared minus 4t minus 5. Okay, so not atypical scenario. Just imagine a straight line and an infinitely small little particle is just kind of moving to the left, moves to the right, you know, it changes its direction, its velocity. Just keep things real simple for our example here. Part A, while we're learning this, find the displacement of the particle from t equals 0 to t equals 6. And part B, find the total distance traveled. Two different questions here. Okay, let's switch over. So we're told velocity v of t, t squared minus 4t minus 5. find the displacement from t equals 0 to t equals 6. Okay, when they ask for displacement, right, that's simply the net change. That's simply the definite integral. So all we got to do is find the definite integral of our velocity from 0 to 6. Okay, let's check it out. 0 to 6, t squared minus 4t minus 5 dt. Antiderivatives 1/3 t cubed minus 2t squared minus 5t, evaluated from 0 to 6. And we're going to plug these in. Let's see, 1/3, 6 to the 3rd minus 2, 6 squared minus 5 times 6, minus plugging in 0. Hey, nice to plug 0 into a polynomial like this. Make our work easy. Okay. Kind of keep in mind, what are we doing, right? Just to draw it all the way back to the net change theorem, right? This was our velocity. This is our position. So this is our ending position, just to note. And this was our starting position. So how far apart are they? That's all we're asking for with displacement. Well, let's calculate. 1/3 times 6 to the 3rd minus 2 times 6 squared minus 5 times 6. I got negative 30. And of course, this is 0, negative 30. And if you look back to the question, like what units, that's actually important here. I didn't write it here, but velocity was meters per second. So what would this represent? Negative 30 meters. The negative is important. We went back to the left. You know, I suppose you could answer 30 meters, but the negative tells you which direction that was. All right. So we started here at 0 and we ended up at negative 30. So there's our displacement. Okay, very nice. Part B. Find not the displacement this time, but the total distance traveled from t equals 0 to t equals 6. I think, well, what's the difference between those? Okay, so displacement is real simple. Starting compared to ending, how far apart are they? The total distance traveled, we're going to take into account maybe the particle, you know, even stopped and changed directions. It could be that the particle started here at 0 and moved directly here across those 6 seconds. Or it could be the particle moved a little bit this direction, turned around and went back. Well, that would be, we'd want to add up all of that in the total distance traveled. Or maybe, you know, it went beyond and then came back that way. It's possible. We need to ask, did the particle ever change direction? Right? If it didn't, then we know it just went directly there. But if it did change direction, that's going to help us figure out the total distance traveled. Did it ever change direction? How would we know? Did the velocity ever equal 0? If the velocity was ever 0, we know it changed direction because it might have moved, slowed down, stopped for just an instant, and then started going the other way, maybe. Okay, let me grab a new piece of paper here, keep going. The velocity, we've got it way back at the top. t squared minus 4t minus 5. Did that ever equal 0? And remember, we only care about equaling 0 in our time interval. Should probably say that. Did the velocity ever equal 0? Between 0 and 6. Let's see, I think this factors. Let's see, t minus 5, t plus 1 would get that for us. So t minus 5 could equal 0, or t plus 1 could equal 0. Yes, it did change directions twice. And one of them was at 5 seconds. We can ignore this one. Ooh, okay, interesting. Now, here's the thing. We don't know what happened. Did it go this way for the first 5 seconds and then go all the way back this direction in the last 1 second? Maybe more likely it went this way for 5 seconds and then turned around for that last 1 second. It doesn't matter. We don't really need to know. What we're going to do is find this. Notice we need absolute values. Total distance, we're thinking just positive distance. So we're going to find the absolute value for the first 5 seconds, and we're going to add the absolute value for the last 1 second. Okay. Let's find this one. I'm going to ignore the absolute values just for the moment. I'll know if we get a negative answer to make it positive. Okay, so this is 1/3 t to the third minus 2t squared minus 5t, this time from 0 to 5. Let's see, plugging in. Minus, hey, guess what? Plugging in 5, when we plug in 0, it's going to be 0. Let's just do that. Plugging in 5, let's see, 1/3 times 5 cubed minus 2 times 5 squared minus 5 times 5. I got negative 100 over 3 minus 0, gonna be that. Okay, so it's negative. So we know during the first 5 seconds, the particle went 100 over 3 meters. Perfect. How far did it travel during the last 1 second? Now, notice it's the same antiderivative, which is nice. We're plugging in different numbers. Okay, 6. Let's see, we already did that once, but okay, I'll just write it out again. We did it once in part A. And plugging in 5. Well, we just did that, didn't we? What did we get before? When we plugged in 6 earlier, it was negative 30, right? And just now plugging in 5 was negative 100 over 3. So what does that tell us? Negative 30 plus 100 over 3. Got 10/3. Okay, that one, it is moving in the positive direction to the right. So what's our answer? We're going to add these two. 100/3 plus 10/3. This particle traveled 110 over 3 meters total. what happened was the first 5 seconds, it went this direction. So negative 100 over 3. That's negative 90 over 3. So it overshot it just a little bit, and then it came back. And so the total distance, 100 over 3 and 10 over 3, 110 over 3 in the end. Okay. Hey guys, that's it for net change. That's it for 5.4.